Lewis structures. Lewis structures show how electrons are arranged among the atoms in a molecule, specifically the valence electrons. Because we skipped the whole discussion of electron configurations, we need to just talk real quick about what valence electrons are. We can tell how many valence electrons an atom has by looking at its position in the periodic table. So the number of valence electrons, abbreviate that VE, valence electrons, not victory in Europe. VE, number of valence electrons, will equal the group number. How's that for convenient? So oxygen in group 6A has 6 valence electrons. Potassium is in group 1A. Guess how many valence electrons? 1. Okay. Chlorine, group 7A, 7 valence electrons. Valence electrons are the electrons on the outside. So real simplistic model of the atom, which isn't actually true, but I'm going to give you some idea. So we can think, originally, one of the early models of the atom was like the solar system, where you have the nucleus in the middle, and the electrons are actually orbiting in circular orbits. We now know that's not true. It's a lot more complicated than that, but we don't need to go there in Chem 10. But there's a certain number of electrons in this level, and there's electrons in this level, and there's electrons in that level. The valence electrons are the electrons in the highest level. They're going to be farthest from the nucleus, and they are the ones that are involved in bonding. So those are the ones we want to look at. The rest of them are called core electrons. I won't quiz you on that, and they're just on the inside, and they just kind of stay there. It's the ones on the outside that do stuff. So oxygen has 6 electrons in its largest shell. Potassium only has 1. So we just look at the periodic table, and that tells us how many valence electrons. So the atoms are going to react with each other in such a way, they're all trying to get 8 valence electrons. How many valence electrons do the group 8A elements have? 8. So we've got neon, argon, krypton, xenon, radon. Those are the noble gases. They don't react much. They make almost no compounds because they have 8 valence electrons. That's like the magic number for atoms. You want 8 valence electrons. Of course, helium's in group 8A. Does helium have 8 valence electrons? How many electrons does helium have total? 2. Okay, because helium is the baby brother of the noble gas family, or maybe it's the baby sister. But with a name like He, it's got to be a guy, right? That would just be wrong to have it be a little girl named He. That was supposed to be funny, but it wasn't. He, now it's funny. So that's an exception. Helium has 2 electrons. Hydrogen also is an exception to almost everything, and hydrogen's really small. So hydrogen's just trying to be like helium. And so we have the octet rule and the duet rule, which I believe there's going to be another slide about. Octet rule says that they react to get 8 valence electrons. An octet is 8, right? A duet is 2. 2 people singing a duet, 2 people. So duet rule for those little guys that can't handle the 8. So how does this work? Well, if we look at potassium, potassium has how many valence electrons? 1. It's in group 1A. So when potassium becomes an ion, we also learned it formed a 1+ ion, right? So potassium forms a 1+ ion by losing that 1 electron. So potassium had 19 electrons total, and now it has 18 because it lost 1. What element has 18 valence electrons? I'm sorry, 18 electrons. Argon. Argon's a noble gas. How many valence electrons does argon have? 8. When potassium loses 1 electron, in terms of its electron structure, it's the same as argon. It has 8 valence electrons, and from the outside, he looks like he's got everything together. Does that change who potassium is? No, because you can't change who you are by changing your clothes or changing your hair or doing anything like that. Your soul. Pardon me?
Lesson of life.
Lesson of life, yes. Lesson of life from chemistry. You can change your appearance, but you can't change who you are, you know. You could have cosmetic surgery. You could make yourself look like whoever your big idol is or whoever you think is really awesome, but you do not become that person, right? You just look like them. And that's what happens with these elements. So potassium becomes an ion. It loses 1 electron. Now on the outside, it looks like argon. And so in my crazy chemistry imaginary world, the noble gases are that in-group in high school that everybody secretly at least wanted to be part of. And they wore just the right clothes and they went to all the right parties and all that stupid stuff, right? We now know that that was just kind of lame. But at the time, it seemed really important. So potassium has this extra electron. He's like, if I could just ditch this electron, then I could look like argon and they'll let me in. You know, I'll be cool. I'll be happy. We're all trying to be happy, right? So potassium loses an electron to become like argon, and he gets happy. So bromine, let's look at bromine. Bromine's in group 7A. The group 7A elements have 7 valence electrons, but they want 8. So what bromine does, he's like, well, I could lose my 7 valence electrons, but that would be a really big change, or I could just get 1 more electron, and then I'll have 8 valence electrons. So bromine has 35 electrons total. If it gains 1, it has 36 electrons. On the outside, it looks like krypton. How cool is that, right? Krypton. Even defeats Spider-Man, Superman. Get my superheroes mixed up. So bromine will tend to form a -1 ion because that gives it the same number of electrons as krypton. And so here we see bromine over here. And these dots are representing the valence electrons. Potassium isn't showing any because its 1 valence electron was taken away. Where did it go? There's no, home for homeless electrons where you can just, like take them to the pound or something, right? And you can't just adopt them from nowhere. Well, potassium's 1 electron was given. How did I do that? Oh, you guys can't see that. That's good. I did some lassoing thing by accident. The 1 electron from there we go. The 1 electron from potassium was given to bromine. So they're all trying to be like the noble gases. And so they're going to either transfer electrons or, as we'll see, they will share electrons to become like the noble gases. So the group number gives us the number of valence electrons. That example was one of an ionic compound. What happens when, that's a transfer of electrons, which we mentioned that before, that ionic bonds are a transfer of electrons. Covalent bonds are sharing. So if you have 2 fluorines, look at this fluorine, he's in group 7A, he's got 7 valence electrons. Is he happy? No. Here's another fluorine atom, he's got 7 valence electrons, he's not happy either. Like, I want 1 more electron so I can look like the cool kids. I just need that certain hat or those shoes or whatever. Just that one other thing that I'm missing. And I'll look like the cool kids and then I'll be happy, right? So this fluorine says, hey, give me an electron. And this fluorine says, no way. If I give you 1 electron, then I'm worse off than I was before. That's not happening. You give me 1 of your electrons. And this, no, I don't want to do that. And they're arguing with each other. And then they realize, hey, wait a minute, what if we share? So they get together and they share electrons. And now this fluorine has the 7 electrons he brought, but he's also getting to share one of the other fluorine's electrons. Because shared things belong to both people, right? My husband and I have 6 children. And yes, they're all ours. And, but if you ask me, hey, Mrs. K, how many children do you have? 6. And you ask him, how many children do you have? 6. But how many total children are there in the house? There's only 6, thank goodness, not 12. Because those 6 children belong to both of us, and so we both count them as our own. So in this covalent bond, this fluorine counts the shared electrons as its own. It's like, hey, I'm good now, I've got 8 valence electrons. The other fluorine also counts those electrons as its own. So even though they only had 7 each, when they get together and share, things are better. Another life lesson, sharing is good.
So all the diatomic molecules are covalent?
Yeah, all those diatomic molecules, those diatomic elements. Remember horses need oats for clear brown eyes? 4, fluorine. Fluorine forms diatomic molecules because in doing so, it becomes more stable. They're not actually happy because they're inanimate objects. They don't have feelings. But this situation is a lower energy, it's a more stable situation. And when they share the electrons, they become more stable. So more stable is more happy, right? So the bonding pair is shared between 2 atoms. Then we also have unshared pairs. So not all of those electrons are shared, right? So these guys aren't shared, and those guys, and those guys. And these over here, and these, and those. The ones that are not shared are called lone pairs because they're alone, right? How sad. They're not involved in bonding. The octet rule tells us that all of the atoms except hydrogen are going to be surrounded by 8 electrons. 8 octet, right? 8's the magic number. Any questions? So we're going to learn how to write Lewis structures, and we're going to practice in lab today. We're doing a modeling lab where we're going to build some things and draw some pictures and play with toys. It'll be fun. So these are the steps for writing correct Lewis structures. First, you need to sum or add up the valence electrons from all the atoms. In a Lewis structure, we only show the valence electrons because those are the ones involved in bonding. So we need to figure out how many electrons can we show. And then we're going to use a pair of electrons to form a bond between each pair of atoms that are bound together. Because if there wasn't a bond between them, they wouldn't be part of the same molecule. So there has to be at least one bond. And then we remember the octet rule. So atoms usually have noble gas configurations. So we're going to arrange the remaining electrons so that everybody gets 8. Or 2 for hydrogen. So let's do an example. Let's do water. So the first thing we have to do is figure out how many valence electrons are there in a water molecule. And so we look at each of the atoms. Well, how many valence electrons does hydrogen have? It's in group 1. It has 1. It only has 1 electron. Its 1 electron is its valence electron. We have 2, that's not the color I wanted. We have 2 hydrogens, and they each have 1 valence electron. How many valence electrons does oxygen have? It's in group 6, it has 6. So 2 times 1 plus 6, so we have 8. So we have 8 valence electrons. Okay? Any questions about that? It's not too hard. So step 2, use a pair of electrons to form a bond between each pair of atoms. So this is where things get a little hard to tell you hard and fast rules. So we've got 2 H's and an O, and we have to figure out how to put those together. The nice thing about the model lab is we picked molecules that you can only put together one way with the kit. And so you don't have to worry about this too much. And on the exam, I will give you ones that are not crazy ones, okay? So hydrogen is a little guy. He has one electron. He's only trying to get 2 electrons. 2 electrons is 1 bond. The hydrogen is never going to be between 2 other atoms. So we're never going to see this. We can't see that. We can't put hydrogen in the middle and have a hydrogen on one side and an oxygen on the other. Because this hydrogen can't handle it. He just can't, okay? He's shooting for 2 electrons, and 4 electrons is way too overwhelming. So that's not good. So that's not going to work out. So we need to put the oxygen in the middle and the hydrogens on each side. And most of the molecules, they tend to be symmetrical. Okay, so if you've got one atom of one element, that's what I meant to say, and several atoms of a different element, the one that you only have one of is going to be in the middle, and the others are going to be scattered around it. So here we have 2 hydrogens, 1 oxygen. Good bet to put the oxygen in the middle and put the hydrogens around it. So there's a pair of electrons. Each of these lines is a pair of electrons. Another way to think of it is that's a shared pair of electrons. Let's see if I can adjust this. So it's a pair of electrons, and they're both sharing, and so it's like we took and connected the dots. So a line is 2 electrons. Important to remember that. And then we need to remember that atoms usually have noble gas configurations, or 8 electrons around them, and so we're going to spread the rest of the dots around to make that happen. So we've already looked at water, and we decided that it was like this, and we figured out. So now what do? We don't have enough. Well, when you don't have enough, that means you have to share more. So instead of oxygen and carbon just sharing 1 pair of electrons, they need to share 2 pairs of electrons. We need to double up, okay? So what I'm going to do is I'm going to take one of these lone pairs, and I'm going to move it to become a bonding pair. You see what happened there? Before, only that one oxygen had an octet, and now the oxygen and the carbon have an octet, because here this guy has 2, 4, 6, 8. And this carbon now has 2, 4, 6, 8. But this oxygen only has 6. So we're still short of dots, and so we need to share some more. Now, obviously, this is not what happens when a molecule forms. It's like, hey, how can we share our dots so that we can all be happy? No, it just does it. But this is how we describe it, however weird that may be. So let's take this guy, this pair, off of the carbon. So when you don't have enough electrons, then you remove lone pairs and turn them into bonding pairs. So I'm going to have that pair be shared between these 2. Now everybody has 8. 8 valence electrons. And we've got the correct number of electrons. There was an earthquake in Japan.
For real?
For real.
Really?
Yeah. I just got a thing on my phone. Magnitude 7.3 earthquake strikes off Fukushima region of Japan. Nice.
Okay, so what does that mean in terms of, what does that mean? This got to mean something, right? It has a single bond compared to a
Right.
double bond?
This is a double bond. A single bond is sharing a single pair of electrons. A double bond is sharing 2 pairs of electrons.
But what does that allow it to do or not to do?
Well, it allows these three atoms to gain octets where they couldn't if they only made single bonds. We can observe that this is actually true. A double bond is actually shorter and stronger than a single bond. So then, like the bond between me and my husband with 3 pairs would be a triple bond. 3 pairs of children, we must have a really strong bond, right? So it pulls you closer together. So the carbon and the oxygen have a double bond between them.
So does that make it harder to?
It does affect its reactivity. It affects its reactivity. You had a question?
Yes, so what makes a double bond is the 2 lines or the 4 dots between the 2 atoms?
Right. The double bond is the 2 lines, which represent 4 dots. It's 2 pairs. That's the double. 2 pairs. A single is sharing a pair of electrons. A double is sharing 2 pairs of electrons. And we'll see that there's also a triple bond, which is sharing 3 pairs of electrons. Any other questions?
So is that the end result?
This is the final Lewis structure, yes, for carbon dioxide.
So it doesn't have to be.
Now, it doesn't have to look exactly like that. If you put your lone pairs in different positions, or if you did it like this, it doesn't matter where you put the lone pairs, as long as they're on the correct atom. So the difference between these two is here there was a lone pair on the side, and down here I drew it on the top. And it doesn't matter. There are 2 lone pairs on the oxygen, and it has 2 bonds, a double bond with the carbon. And over here I drew them differently than up there, and that's fine.
But we only have 6 and 6 and 4. We don't have.
But the line is 2.
Oh, because there's.
See,
sharing.
this one, it's 2 dots.
I'm still separated.
That's okay. That's okay. So let's just, let's do green. Okay, so the oxygen, consider all of these electrons to belong to her, or him, it. This oxygen counts all of those electrons. And the carbon counts all of these bonded electrons. Does that help?
Yes.
So the bonding electrons get counted by both atoms. Just like my husband and I both count all the children. Even if one's being naughty. Yeah, he's still our kid. Any other questions? So a single bond is a covalent bond in which 1 pair of electrons is shared. There's the example, hydrogen, hydrogen. A double bond, 2 pairs of electrons are shared. A triple bond is 3 pairs being shared. And that can happen. It doesn't happen as commonly as double and single, but it does happen. And a triple bond is going to be stronger and shorter than a double bond even. That's just for your information. I won't test you on that. But you should know that a single bond is a single pair. A double bond is a double pair. A triple bond is a triple pair. Triple pair. Triple pair. I'm not going to test you on these at all, but I do need to tell you that there are some exceptions to the octet rule. You have a question?
Well, I would probably get.
Is it only certain elements that can make double bonds, or is it just how math works out?
That's a good question. That's kind of a cause and effect issue. Like nitrogen, it's not unusual for it to form triple bonds, whereas something like bromine will almost never form a triple bond. And that has to do with how their electrons are paired or not paired in their valence shell. So that gets into kind of some stuff we don't want to go into. But we won't really have to think about that too much. But, nitrogen does not always form triple bonds, but it can. It does so when it needs to. So some exceptions. Boron is one of the little guys. He's not as little as hydrogen and helium. but he's not as big as the rest of them either. And boron tends to form compounds in which he has less than 8 electrons. He tends to form ones where he has 6. And so he's like settling. You know, yeah, everybody else wants 8. I'm just not even good enough for that, so I'm going to settle for 6 electrons and be happy with that. So that's an exception. And there's an example, boron trihydride. That does not satisfy the octet rule. But that compound exists. It has 6 valence electrons, and there can't be an octet on boron. There's just not enough electrons.
So the original hipster.
Pardon me?
The original hipster.
I guess so. The original hipster. Another exception is molecules containing odd numbers of electrons, like NO, and NO2, NO, and NO2. Got to have some fun in life. How many valence electrons does NO have? Well, nitrogen has how many? 5, and oxygen has 6, and that adds up to 11. You can't arrange those in pairs. You just can't. So you can't have the octet rule be perfectly satisfied. There's no way. And NO2 is also odd. It's going to be 5 plus 2 times 6, or 17. Again, odd number. There's going to be an odd electron somewhere. So just know that those exist. Draw a Lewis structure for each of the following molecules. And yes, I know I'm going over, but we have lab next, and so that's what we do. BF3. Let's not do that one. That violates the octet rule, and I just said I wasn't going to make you do those. Well, carbon dioxide we already did, so that's done. Let's do carbon tetrachloride, CCl4. I have to revise these slides. So carbon has how many valence electrons? 4. There's 1 carbon. There are 4 chlorines, and they each have 7. Thank you. So we have 32, right? We'll put the carbon in the middle and the chlorines around it. And then we need to have a bond between them. There has to be at least a single bond to hold these guys together. We have 32 electrons, that's a lot. So we count the bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Nice, came out even.
Is there a mathematical way to figure this out?
Probably. I think that would involve way too much thinking.
But isn't that kind of a mathematical way of figuring it out?
Well, you can look at the 32 and say, well, 32 is evenly divisible by 8, and it gives you 4. So there must be these 4 things with 8, and then they're sharing with the carbon. And yeah, there is some math you could do with it, but that's like playing chess, okay, which some people love, and they want to think ahead in all these different angles and think about all of that, and it's like, I don't think that's fun. I'm not going to give you hard ones, no.
Because I'll be erasing. I need the paper.
Use pencil. Use pencil. Okay, so that's carbon tetrachloride. Everybody has 8 electrons. Let's do cyanide. I'm going to do him up here. Cyanide. Now this is an ion. We haven't talked about ions yet. We're not going to do a lot with ions, but so carbon has 4. Wrong tool. Carbon has 4. Nitrogen has 5. This is an ion. It has a negative charge. Does that mean it has an extra electron, or did it lose one? It has an extra. So when we see a negative sign, then we have to add that many electrons. This is -1, so we add 1 for that charge, and we end up with 10. Okay, that's better, because that's an even number. Even numbers are good for this. So I'm gonna create some space.
So if it was
Isn't this one a double bond?
positive,
Then you would subtract electrons.
you
Mhm.
And then 6 others around.
So we're going to have carbon and nitrogen. There's only the two atoms, they must be connected. And there has to be a bond between them. So that's good. And then we've got 10 valence electrons. So we already used 2, 4, 6, 8, 10. We ran out. Not enough electrons. Then we need to share. We need to make multiple bonds. So what we're doing is we're taking these guys and we're putting them in here. That didn't work so well. Okay, let's do it this other way. Yeah, we'll do it that way. That'll work. Okay. So I moved one pair in here. Are we good? No, we're still short, aren't we? So we need to move another pair. So we'll take one from the carbon and move it in here and make a triple bond. Now, they're sharing 6 electrons, so they each have 6 from the shared electrons, and they have the one lone pair, so they each have 8. But this is an ion. And the way we show ions is we put brackets around them, and we put the charge on the outside. Because a compound with 1 carbon and 1 nitrogen is going to have a charge, we have to indicate the charge somewhere on here. Otherwise, it would be wrong. So it's an ion. Any questions?
And it's an ion
Because there was a charge on it.
what is the other one we did? The carbon and the chlorine.
The carbon tetrachloride is a molecule, not an ion. It doesn't have a charge. See, we look at the formula down here. The formula down here. And there's a charge on it, Cn minus. So we can draw Lewis structures for some of those polyatomic ions, phosphate and sulfate and nitrite and hypochlorite and all those guys.
With it being just a regular bond without being an ion, would it be the same Lewis structure just without one of the electrons?
Yeah, if this was not an ion,
Just one of the lone pairs would just end up being one electron.
yeah, we'd get rid of this, and we'd have to get rid of one of those, and that's not going to be very stable because it violates the octet rule. Because carbon's not happy or nitrogen's not happy. Somebody's not going to be happy. So that would be if.
so as a chemist,
Mhm.
you just see that.
Mm-hmm.
And what does that tell you about that compound?
It tells me all kinds of things. I can look at that and tell you the shape of the molecule. The carbon tetrachloride has a tetrahedral shape. The cyanide ion has a linear shape. It tells me that carbon tetrachloride is nonpolar, that cyanide is polar. There's all kinds of things. I mean, for such a simple concept, just making dots and drawing lines, you can look at that and actually know a lot about the molecule.
Since cyanide is polar, wouldn't one of those electrons be actually if they were on nitrogen?
The cyanide is an ion, but the whole thing has a -1 charge together. And so it got an electron from somebody else.
But since it's polar, wouldn't one side of the molecule have a more negative charge and one side be more positive?
Well, if you're looking at it, not thinking of it being an ion, the nitrogen is more electronegative than the carbon, and so it would be a little lopsided. But we don't even try to draw them that way.
Okay.
That'd be too hard. Which of the following supports why Lewis structures are not a completely accurate way to draw molecules? You know, this isn't a good question. Because that's something we skipped. Oh, polar versus nonpolar molecules. I think this is, yeah, that's just the very end. We're going to finish this off.